Okay, cool. I wanted to start off the demonstrations that we're going to be doing right now to give you an example of the things that we're doing here at Berkeley that use parallel programming and that take what you've learned in these past few days and kind of apply them in what we think are really cool and interesting ways. And so we're going to have a couple people come up and talk today. I'm the first. My name is Matt Torok. I work in the former UC Berkeley ParLab under the graduate student Leo Mirovich and Professor Ross Bodick. What I've been working on for these past couple of years in my research has actually been doing big data visualization using GPU parallelism. And that's a project that we call Superconductor. So Superconductor arose out of this idea that we need to interactively explore big data. We can have all this data right there, but right now you put it into your statistical analysis software, Excel or whatever, and what you get is a simple yes or no answer or some p-value or something that tells you what you asked, but it doesn't really educate you. What we really need is big interactive data, stuff that we can explore and that we could work with. So let me give you an example of some of the things we've done. So,
how about audio?
I'm sorry?
How about audio-related things? I remember hearing something like an audio data mishmash earlier today.
Yeah, we're actually going to have a presentation on music right after this. So I'm just one part. I'm telling you about the visualization aspect, and other people are going to tell you their interesting kind of part of that. Cool. So to give you an example of one of the things that we've been working on, we started out with a program for doing data visualization on the web called d3.js. And it is kind of the popular way to do data visualization, and it's really cool. But the problem is when you start to up that data. So here you're seeing 100 nodes of what's called the sunburst graph, and it's pretty smooth and it's pretty neat. If we up that to 1,000 nodes, you're still doing okay. Up that to 10,000 nodes, if I can even click it, and all of a sudden, you don't have interactivity anymore. Like you're getting a render, but if you wanted to actually animate this or get information from the animation or interact with this, you're not going to be able to do that. And I can put 20,000 nodes here, but that usually crashes my browser. So we wanted to do something for big data. Big data isn't 1,000 nodes. It's not even 10,000 nodes. It's hundreds of thousands of nodes, millions of nodes of data. So we made the system Superconductor, and we recreated that visualization in our own system. Here that visualization is. This is 1 million nodes running at approximately 10 frames per second live in the browser. All this is local. We can interact with it if we wanted to. We can zoom in or other things if it doesn't crash. And that's just one example. We have a tree map here where we went in and we took data from a recent election and we analyzed it. And we were actually able to view fraud in this election. And the way we did that is because we took data from every single polling place in this entire country, 95,000 polling places. We put it into this visualization. You're seeing every single polling place right here. And then we analyzed that, and we're actually able to see kind of interesting patterns in the data that we didn't see on the raw data itself. So, going back. So to kind of sum up, what we do at 1 million nodes, D3 does at 10,000 nodes on a good day. We're about 2 magnitudes order of speed increase over them by using this GPU parallelism. But there's this kind of tension here between an efficient programming language and a productive programming language. You kind of want both. So how do we allow you to do this GPU programming, this kind of very specialized stuff that you learned over here in the past couple days, but you guys are very smart people. How do we make this so everybody can use it? So that's kind of what we did with Superconductor. With Superconductor, we identified 4 main tasks for doing visualization. You have your data, you want to style it, you want to lay it out and render it, and all this you can kind of think of as in Excel. But most of the talk that we're going to be talking about today will be in the layout and rendering step. How do we take your data and make an image out of that? So we want to do a scalable language support for each one of these. Basically, we're going to attack it by creating programming languages. So for doing data, we have JSON, which is a standard JavaScript way of doing big data or analyzing data. You use CSS selectors, you have JavaScript. For layout, we come into a problem, though, because all those existing tools, they work well. But for layout, HTML and JavaScript, as we just saw with D3, those are too slow. The browser is just not quick enough to actually be able to do data visualization with those. The browser is largely single-threaded. The entire page runs in a single thread of execution. So that means that if you have a JavaScript function that takes 5 seconds to complete, not only can no other JavaScript functions execute, but nothing on your web page can execute. You can't scroll, you can't click, you can't see animation. Basically, you lock up the entire page. So you really want to make sure that we're doing parallel and very quick computation here. So to solve this problem, we created a new DSL, domain-specific language, for custom layouts. It's a simple language, but it allows us to optimize that very well. So, and we're sticking to the web programming model as well. So in the web programming, we have, for doing JavaScript and multi-core, you have web workers. But we also have this technology called WebCL, which is a browser-based version of OpenCL that's coming out from the Kronos group. It's a draft standard, but it's being ratified by the same people who make WebGL, which incidentally we also make use of here. And as a kind of a nice little benefit here, OpenCL and OpenGL allow for shared memory, which allows us to do very quick computations if we can keep everything on the GPU. So in our system, in Superconductor, we parse the data, which we do multi-threaded, using web workers, which are JavaScript's version of threading. We have selectors for doing styling in OpenCL. We have layout, which we do in OpenCL. And we have rendering, which we do in OpenGL. So for layout, we had to create this custom DSL, like I mentioned before. So in our system, you write a custom layout and run it through our Superconductor compiler, which in turn generates OpenCL kernels for you. And let me give you an example of that. So this is a simple HBox. You have a horizontal box with 2 other horizontal boxes, and you want to figure out its height, or its width, rather. So your inputs are your X and your Y, and your W and H at the leaves. And so given the X and Y of the root node and the WH at the bottom, we kind of want to go through and solve for all of these WH, X, and Y for all nodes in the tree. So our language is nice. It's local, single assignment. It compiles. And, well, actually, the main benefit of having this restricted language is that we can now compile it to automatically be parallel. We take our simple language, which is just a simple declaration here, like W equal left W plus right W. And that doesn't say anything about the implementation. But what that allows our compiler to do is automatically figure out a parallel structure to this and generate really fast OpenCL GPU kernels. So how we do that is you take your layout that you just wrote. Right here, for example, was an example of that DSL that I was talking about. You run it through our compiler, which finds a schedule of parallel traversals on that data, just basically how can we process this data in parallel. It outputs that, then we flatten our data, and we load it onto the GPU. You don't have to worry too much about the details of that. I'm going to get into that. So our parallel traversals, the way that we exploit parallelism is by doing parallel tree traversals. So for example, in a breadth-first bottom-up traversal, we may solve the width and height attribute of all of our data. Then the compiler may schedule a top-down traversal where we do X and Y, and so on and so forth. So basically what we're doing on the GPU is a bunch of parallel tree traversals. But the programmer, the person who originally wrote that specification of their layout, doesn't have to be cognizant of any of these, because this is what the compiler will actually give you. It will actually figure out that the first traversal should be a breadth first bottom up, and second should be a breadth first top down, and what you can solve in each of those, and so on and so forth. And we output that as WebCL kernels. Now, the data flattening that I mentioned before is kind of how our data structures on the GPU work. So when we're doing, for example, here a bottom-up breadth-first traversal, we do basically a parallel for loop over the entire level of the tree. We then go up a level, process, and go and so forth until we get to the top. So on the actual GPU, these are all laid out in consecutive arrays. So in memory, they're just one flat array structure. And we just tell our kernels to process some subset of that data corresponding to the level it wants to work on, and then it moves on to the next, into the next. And each step, it's synchronizing, making sure the level before or above is completed. And we do this for each element that we want to solve for. So this would be solving for W. The next one could be H, X, Y. The compiler handles all of this, though. You don't ever have to think about these data structures or how this flattening is. You just have to give it your data in JSON, and we figure out the rest. Rendering is also kind of interesting because on a GPU, you don't really have malloc. What we want to do for doing rendering is a malloc. We want to say, OK, we want to draw a circle for this node. This piece of data needs to be represented on screen by a circle. But that circle may have 20 vertices. And you don't know that until you've already solved the layout. How do we then figure out how much data or how much memory to allocate for this data that we want, this vertex data? And the way we do that is actually by, well, dynamic allocation is not the way we do that. But the way that we do that is by actually encoding this system inside the superconductor grammar, by putting it a memory allocator inside our own language. So what we need to do is we first need to sum up the memory needs of the entire tree. So this bottom node may have a rectangle and a circle and a line and a rectangle. We need to sum up how much memory each of those needs to write out as rendering data. And by rendering data, I mean vertex data that we're going to render. Then on the CPU side, once we've figured out that amount on the GPU and summed it up, we allocate a buffer for that on the GPU itself. Then we do another parallel bottom-up traversal to actually fill in that vertex data. So we hand that buffer we just allocated back to the GPU kernels, and then each one of those nodes will then fill in that buffer with whatever they needed in the first place. And finally, we give OpenCL that buffer to render immediately. Because we're keeping that buffer on the GPU, it's just a quick ownership transfer. So there's no data movement whatsoever. So we calculate all this vertex data on the GPU directly from our input data, and then we render that to screen, which is a very, very quick process. And I'll quickly go into interactivity. So animating layouts, you can modify the input data by small intervals and recalculate. You can also do styling, which is a work in progress. We have CSS style selectors where you can actually update the styles of different things. So you can make something red or give it a thick outline or whatever attribute you want to do. But because our rendering and layout loop is so quick, like you saw before, it was about 10 frames a second, we can simply vary our input data in small ways, rerun the animation to get a slightly different graphic, and repeat that over and over again. So to kind of summarize, what we have is a big data visualization language. It's orders of magnitude speed up over regular JavaScript. And to actually make that happen, we have a compiler from our simple language to GPU code and a GPU-based rendering library for doing the allocation and vertex generation. We call this Superconductor. It's available now open source at sc-lang.com. And if you have any questions, I'm happy to answer them. Yeah?
Is the syntax and you know how D3 has made a lot of examples of this and that?
Yeah.
Is the syntax and everything really accessible? Where is it out? I guess you explain to me the website, what does it have?
Yeah, so the syntax for our DSL, the language that we invented, is it's designed to be simple kind of by nature. The trick with it is that it's actually a kind of a restricted language. So when you assign an attribute, you can only assign that once. It's single assignment. You can only access your parents' or your child's data, things like that. So it does take a little bit of kind of a readjustment if you're used to kind of a procedural style, algorithmic way of thinking about things. It takes a bit of adjustment to get to this kind of declarative style that we have. But once you do that, it's actually very, very simple because you're not thinking about implementation details about like what the GPU is doing. You're just thinking, okay, if my children each have a width, I want to sum them up and make that my width. And you start thinking that way. And so it's a bit of a context switch if you're not used to it, but we found people can generally get up and running with it pretty efficiently. Cool. Any other questions?
What happened to the user events that consume too much time?
Can you repeat that?
What happened to the user events that take too much time to process or to complete?
Like interactivity, are you speaking of? So if you click on something and it takes too long for the user, generally you'll probably just drop a frame. So when we're running this kind of animation, like this animation or this system is kind of static until we give it animation or interactivity. So for animation, we just have a event loop that fires every 0.1 second that changes the data and re-renders it. For interactivity, we just wait until the user clicks on something or some event. And that part is actually running in JavaScript because that's not where the heavy lifting is. So all your interactivity, all your interacting with the user is just regular JavaScript. And in turn, that'll actually use our superconductor.js library, interact with that, and tell it, okay, this data is changed, re-render. And then all of the important calculations, the rendering and the layout, those then happen asynchronously on the GPU. So the GPU is never blocking the CPU and vice versa. Cool. Anything else? Yes?
Looking at the website, it says the developer is available only for Apple computers.
Yes. That's our big drawback currently because we make use of WebCL, which, like I mentioned before, is a brand new emerging standard. There is currently only one implementation of WebCL that kind of is complete enough that we can use it, which is Samsung's implementation for WebKit. They recently added a Linux port of that, so you can now run that on Linux. We haven't tried it, but we hear it works. But generally, yeah, you need to download Samsung's special kind of WebKit version, compile that, and then you can actually run Superconductor. But we're working on also backups as well and fallbacks. Yes?
If you want to exploit that that large-scale visualization, and put that on the server,
Yeah.
Do you expect to have like a good GPU for the server computer?
No, that's actually the main benefit of our system. So there are big data visualization tools out there right now, like Tableau and Spotfire and other tools. But what they do is they put all of the actual visualization work on the server. So the client is just kind of this dumb client. It's just getting back graphics and sending back commands to the server. That works in certain aspects, but the problem is you start getting problems with interactivity. You can't do the style of animation and instant feedback that we're doing with Superconductor because we have all that data local. We don't have to hit a server and come back. We also have benefits with scalability because we require no server architecture whatsoever. You just need to be able to serve up a HTML file and a JavaScript file and your data as like a JSON file. That's the extent of what Superconductor needs from the server. And so we kind of think of this as if you're the New York Times and you have millions of readers, but you want to put on a visualization of all the election data from a recent election to show fraud. You don't want to have to buy a huge number of servers to do that. So with our system, by pushing most of the computation on the client, you just serve up that data as data, and the client takes care of actually doing the heavy lifting. So there's no GPU needed on the server whatsoever. Cool.
Music yet or GPU?
I think the next one is music, I want to say. Oh, GPU. Cool. Excellent. Thank you, guys.
All right, that's better. Okay, so I need to plug my machine in here. Okay. My name is Mike Anderson. I'm going to be presenting computer vision applications that we worked on as a part of ParLab, which is the previous project here at Berkeley. This is a lot of people contributed towards this work, and some of them, most of them are listed here, but it's generally, we're called the Palace team, basically all graduate students for Professor Kurt Koitzer. So ParLab is a lab that was hosted here at Berkeley that just finished up. And it was created with this idea that we would be driven by applications, and that would drive kind of our software and hardware development. And one of those applications was content-based image retrieval. So this is where you want to take an image and use it to query a database. The database will return to you images which are similar or related based on the actual content of the image, not metadata or text or anything. So that was our motivating application. And when we looked at it, we found that really, in order to do that application, we needed to look more broadly at computer vision. So we attacked a number of problems in computer vision. And we collaborated with professors here in computer vision like Jitendra Malik, Thomas Brox, and also Jim Demmel. We collaborated with an expert in applied math and computer science to produce efficient implementations of computer vision applications. So today, I'm going to demonstrate 3 of these applications running on a commodity GPU. And that's this box here. There's a NVIDIA C2050 in here, and I'm going to demonstrate image contour detection, background subtraction, and also optical flow. So first, there's image contour detection. So what this is basically we start with an image, and we'd like the computer to generate contours or discontinuities in the image. So we'd like to generate something like the image down there, where if you were to trace around all the objects in the image, you'd probably draw a line around the person, a line around the structure, and maybe the line between the sky and the trees as well. So we want to generate this because it's very useful for analyzing the image. So there's a standard data set and benchmark for evaluating algorithms that solve this problem. And the algorithm that did the best on this data set is called GPB, at least at the time, GPB. And that is developed by Jitendra Malik, as I said, who's a professor here. So what our group did, or what Brian Catanzaro and several others did, was to take the code that these experts had written and parallelized it and wrote it in CUDA, and also did algorithmic improvements to speed it up by almost a factor of 100. So this is the software architecture of contour detection. In general, you start with an image, and you extract features from the image based on the brightness, the color, and also the texture. And you combine those features to form what's called an MPB detector, which tells you for every point in the image, what is the probability that there's an edge at that point. That MPB detector then is sent over to the right, where it's transformed into a large sparse matrix, which is called the pixel affinity matrix, and that's passed into a generalized Eigen Solver. The Eigen Solver is approximating a solutions to graph cuts, normalized cuts, and the eigenvectors that it spits out are post-processed to form the contours. So to visualize that, you can actually spit out intermediate state at every stage in this pipeline. And as you can see, it's very parallel. There's a lot of pixel-wise parallelism. Yeah?
Contour detection is synonymous to edge detection?
There's slight differences. So contours need to be closed is one big difference. All right, so I'm going to actually demo this. We have this running on a GPU. As I said, this is an NVIDIA C2050, and this is the code that Brian wrote. So to demo it, I have a webcam. Yeah, this is very exciting. And I don't know if I should, yeah, I'll do this, take a single shot. And you can see it running here. So it takes about 3 seconds to run. And you can see we get these nice contours at the end. So it's 3 seconds to run. The code that we originally got took something like 4 minutes. So it's a huge speed up. And this code has actually been downloaded over 2,000 times. All right. I'm sorry? So there's a breakdown in that paper of all the time for each stage. Oh, sorry, the question was, does k-means take a long time in this algorithm? There's a breakdown of how much time is taken in each portion, and I can't remember. I know that the biggest portion is for the generalized Eigen Solver, but you'd have to look back at the paper. Okay, so the second application I want to talk about is video background subtraction. So the application is shown down here. Basically, we're given a video, a couple hundred frames, and we want to separate it into static pieces, and which would be the background, and then the moving parts, which are the foreground. So the particular algorithm that we used for this, we got from there was a paper from Stanford in 2009 with an approach called robust PCA. And how that works is basically we take this video and we turn it into a matrix where each column of the matrix is composed of one frame of the video. So we just stretch out all the pixels in the video, and that becomes a column vector. So the height of the matrix is a number of pixels in the video, and the width of the matrix is a number of frames. And the algorithm proceeds by iteratively taking the singular value decomposition of that matrix. And the way that we solve singular value decomposition is using something called a QR factorization, which is also used for least squares. So basically, we need to do the QR factorization over and over on this matrix. And the interesting thing that we did actually was, instead of using the standard QR factorization algorithm, we employed a new communication avoiding algorithm that was developed by Jim Demel's group. And instead of operating like the standard algorithm would on the entire height of the matrix at once, the communication avoiding algorithm allows us to break the computation vertically into chunks so that each small problem can be solved efficiently in cache. So this leads to actually a big speed up. And we can actually see the speed up in this application. So I'm going to demo that next. And I'm going to use my webcam again. Yeah, sorry, I didn't mention that. The question is the camera fixed? Yes. So it's a stationary camera, stationary background. So what I'm going to do is just record a video of myself, and I'll try to have certain portions of me move and others not, so that it'll have something to subtract. So I'll just record 150 for, oh, sorry. I have to close the other window. Okay. So I'll just record 150 frames, and I'm kind of moving my hand, hopefully keeping the rest of me constant. All right, so first thing I'm going to do is try to solve, run the algorithm using the traditional QR factorization. So I wrote this as well, and it's running on the GPU. And as I said, it's iterative, so we're doing a QR during every iteration. The residual is going down, and the objective function is going down as well. That's a good sign. And I'm running it for 100 iterations. So on the left is the original video, and in the middle is the foreground, which should have the moving parts, and on the right is the background. So
it's a ghost.
Exactly, it's a ghost. So that was a traditional approach, and this was, if we run it using the communication voting algorithm, which is our kind of special contribution, you can see it's running about 3 or 4 times faster. We get the same result. So that was very exciting. And just for comparison, those are both on the GPU. If we run it, there's a multi-core in here as well. We can run the same problem using Intel's provided library called MKL. And in this case, we get about 1 iteration per second. So this is a huge difference, and you can imagine it would be hard to make it real time using this library. But I won't let that finish.
Is that the floating point?
Yeah, so this is using single precision floating point. And the video is 320 by 240, I think. Okay, so that was 2. I have a third thing, demo. So the third problem is optical flow. And so what we did at the end of the ParLab, we wanted to integrate all of our technology. So we created this vision-based musical instrument. So the idea was we'd have a drum, and we'd do a video capture of hands moving over the drum. And then we would use an algorithm called Optical Flow to compute motion of the hands, so the direction that the hands were moving and their velocity. Then we would use that information to generate audio, and synthesized audio, which was a process created by our audio experts, our music experts. So the whole big idea here was this actually demonstrates a lot of our ParLab technology working together. So a lot of these things I'm sure you haven't heard of, but CJITs is our kind of compilation flow, and tessellation was our operating system. Also, this was running on our own chips, our own silicon, and using communication voting algorithms, and also kind of featuring our work in parallel computer vision and signal processing. So the optical flow, as I said, computes direction and velocity for each pixel across 2 frames of a video. And we're solving it. There's many different ways to solve it, but we're solving it using an algorithm called Horn Chunk, which is very simple, but we're able to make this real time. So what that boils down to is a sparse linear solve. So we're solving AX equals B, where the matrix is 2 coupled 5-point stencils. That structure is shown down at the bottom. And we solve this linear system using communication voting conjugate gradient algorithm. So I'm going to demonstrate that now, solving optical flow using communication voting CG, again on the same GPU. And this is actually written in OpenCL. So we don't have a drum, but I'm just going to pass my hand over the frame of the video. So there's no noise when there's nothing, no motion, so that's a good thing. So the colors in the visualization indicate the direction that we're moving, and the intensity is the speed. So if I move faster, And also the audio that's being synthesized is different depending on the speed and direction. So when I move my hand faster, it is a higher pitch. All right, and so you can see when I quit, we're getting 30 frames per second on that. Yeah, so segmentation fault, that's a feature, yeah. Okay, so to review, I wanted to demonstrate our ParLab applications. Our application was content-based image retrieval, but that really broadened into computer vision in general. We had these productive collaborations with the vision professors here and also Jim Demmel. I demonstrated contour detection, background subtraction, and optical flow. But there are also many things that I didn't demo today that we also did, and if you're interested in these, then let me know. But we've done work in high-quality optical flow and point tracking, video segmentation, object recognition, human detection, and also many more. And also things outside of parallelizing applications outside of computer vision. So thank you for your time, and any questions?
How about we move on to music? We have a little, around 20 minutes left.
All right, great.
I saw on the slide you mentioned the audio graph signal processing. What do you mean exactly by that?
So actually, in the next talk is going to be David Wessel, and he is the music expert in charge of that portion. And in this case, it was using the programming language Faust to generate that audio that you just heard. Yeah.
Demo, there's still a lot of problems that we could just start applying demo stuff to that hasn't been applied yet. Is that the implication?
So the question. Oh, sorry, you have the mic. Definitely, I think this particular problem with the SVD and the background subtraction was particularly well suited for the communication avoiding algorithm because of the height of that matrix and the really skinny width. So it's kind of a classic case where this does really well. But there's many others. Basically, anything that does a linear solve, you can show some benefit. All right. Thank you.
Okay. All right. So I'm going to say something about a few of the musical applications that we worked on during the last 5 years when we were associated with the ParLab. I might say it by way of introduction. I'll acknowledge a lot of people near the end and along the way, but there are many people involved in some of this work. And I want to put in a plug for our own center, which is the Center for New Music and Audio Technologies. We're at 1750 Arch, and at the end and on the slides that you should have received, you'll see a website. So you can see in more detail what we've been doing in the area of just applying computer technology to music. So here are some of the application areas that we worked on. Well, and I would say the main one is the new computer-based musical instruments and so on. And I'll spend most of my time talking about that. And I'll say something about some work we've done with high channel count audio speaker systems and so on. We've worked on hearing aids with Starkey Labs, and computer-aided composition as well, and music information retrieval, which I unfortunately won't say a great deal about, but it was also a very important project in the music group and in the ParLab as a whole. So I think what's really important to recognize right at the very beginning is that there's a lot of parallelism in music. If you, for example, look at an orchestral score, you could see many lines which are operating in parallel with most often very little communication among the lines. So this fits this data parallelism very, very nicely. And you might say that sometimes it really looks embarrassingly parallel. But on the other hand, there are some real challenges that I'll say a word about now. And the main challenge, which we'll come to, it has to do with maintaining interactive, reactive, low latency behavior in the system. Well, when we came at first to the ParLab, it was a kind of like a quiz. They had already identified a number of computational motifs or dwarves, which I'm sure you've heard about in the course of these days. And when I was there with Dave Patterson and Kurt Kreutzer and so on, they said, well, do you guys use any of these computational motifs or the dwarves? We said, yeah, I think we use almost all of them in various applications. Certainly spectral methods are very important. Dense and sparse linear algebra, structured and unstructured grids are used in physical modeling. We do a lot of machine learning, and there graphical models play a role. Let's say we want to align two pieces of music. Well, dynamic programming can play a role, and graph algorithms as well. And we like to compute transcendental functions, and that wasn't among the early set of dwarves and motifs. But so we were right in the pocket with the kinds of things that the ParLab was interested in, and our goal was to get them done in real time. Now, there are some patterns. I'll spend some time doing a little pattern mining at the end on a particular application. But here's a list of some of the patterns that we were inclined to want to optimize for specific musical applications. So let's talk for a while now about the new musical instruments and so on. So we want, first of all, computer is the sort of primary element in these systems, but I'm going to add a bunch of things to it in a moment, some sort of controller and interfaces, so on. But the main design criteria are we want bodily engagement. I mean, we're really interested in playing these things and interacting with them in a real-time way. We want them to be musically expressive and inspiring and easy to play at the beginning. But we want them to be constructed in such a way that they would be accepting of a lifelong investment and development of virtuosity. I'd like to build instruments that I'll play until the very end of my abilities to play. Okay, so let me just give you an outline here of how I think about instruments. Again, I'm going to stay away from the left-hand side of the graph. There's a whole story about the cognitive science associated with performing on instruments, and I'm very interested in that. We have a research program in that area over at the Center for New Music and Audio Technologies. I'll start with the hands there. They oftentimes interact with sensors of some kind, touch sensors. The instruments that we've been particularly interested in involve surface performing on a surface of some kind. And so things like multi-touch play a big role. So we've got to somehow get data from the user in the form of gestures. In other words, I like to think of these instruments as things that you would, in some sense, caress or manipulate in a very intimate and refined way, as you'd find on a violin or a viola and other traditional acoustic instruments. So they have to do some gesture processing. Now, the gesture processing often involves sensor fusion, that is, taking information from multiple sensors and combining it in such a way to act upon a algorithm that's running in some kind of control system of some kind that controls the algorithms that you're using to produce the sound. Now, here you see that I've got a few dimensions or a few arrows going into the controller and lots of them coming out. So this is a kind of transform that goes from a low-dimensional space to a high-dimensional space. And you know, look, we just can't do that without building some sort of correlations into the high-dimensional structure of some kind. And so we've thought a lot about moving from low-dimensional control to high-dimensional structures, and there we've made some really interesting use of some machine learning techniques and so on to find out or to set up these situations that we that in fact would privilege this kind of arrangement. I, for example, often have 100 oscillators associated with each finger on a touchpad that has an X dimension and a Y dimension and a depth dimension. So I've got 3 dimensions of control for 100 oscillators. The oscillators have frequency parameters associated with them, 100 of them, and 100 amplitudes. And sometimes we don't worry too much about the phase, but let's say we have the phase, so we could have as many as 300 parameters to set up and derive that from 2. So we need to build in a lot of structure into those. And we think of that often as a kind of active composition, actually determining how gestures relate to final outcome. Of course, in the end, we evaluate everything from a perceptual point of view, and we want the human performer in this case to be able to explore, and so we want the software that we build in the instrument to invite exploration, to afford exploratory control, and so on. So latency is the really an important thing. And I'd just like to lay out some numbers here because different situations call for different takes on what the latency should be. If we're thinking about channel alignment, let's say for spatial audio, we really have got to get under 5 microseconds. Now that may seem crazy, but it isn't. If you think about the distance between the 2 ears and the speed of sound, well, let's say we're about 6.5 inches between the 2 ears, and now we're looking at our ability to localize in the front. We're accurate to about 3 degrees in many experiments that can demonstrate that. When you run that down, that's down in the sub 10 microsecond range. So that level of synchronization is important. Audio input to output, we'd like that to be as low as 1 millisecond. In fact, if we could do better than that would be great, but we do have to get some computation done. But why would that be the case? So if you think about, let's say, the hand moving towards the surface can be traveling at quite a speed, maybe 60 miles an hour, and would strike the surface, and depending on the shape of, let's say, the finger configuration or the shape of the hand, we're going to end up with things that resemble flams. This is where a drummer plays with 2 sticks, and he times the arrival of the 2 sticks by how far they are apart. So you can actually achieve this under 1 millisecond latency between those two. And that turns out to influence the quality of the sound. You hear it as one event, but different delay times have different qualities associated with them until they get to over the 30 millisecond limit or so, and we start to hear 2 things. Gesture to audio. A guitar player, you can think of it this way. If I have my amp at about 10 feet away or just from my guitar, then there's an actual 20 millisecond delay between when I pluck the guitar and when I hear the sound back. So because sound travels about a foot, 1,100 feet per second, and so I'm hearing just from the sheer distance certain kinds of delays. Well, I would say 10 feet away is most guitarists would not like that. They'd prefer maybe 5 or so and put us under that 10 millisecond delay. And I won't spend much time on the rest of this, but one thing I want to emphasize that's very important, is that audio jitter is extremely degrading. Put it that way. It really does have a bad influence, and in fact, the signal-to-noise ratio really can go down if there's some irregularity in the clock or the timing of the samples as they come out. Video is much, much more tolerant. Now, here's another important concept. Just because something computes quickly or has high bandwidth does not mean we're going to have low latency. In fact, one of the problems with GPUs for most of the musical applications that we've attempted to where we really try to keep the latency down, we've had trouble getting things in and out of the GPU in a satisfactory manner to keep the latency low, even though the computational bandwidth is fairly high. Think of it this way. If your computation involves computing over a large array at one time, then you could see that then the latency is going to be limited by the size of that array. So we have to have small algorithms that operate on small bits of data, and also we want to keep the I/O buffers on our instruments as small as possible. And sometimes that's a real challenge. So latency is a big challenge. Here's an example of an instrument that we built. I want to acknowledge Adrian Fried here and Remus Avizenius, who played a big role in this. This instrument has 32 touchpads on it, and each of those touchpads is sensitive to one point and there's an X dimension, a Y dimension, and a pressure dimension as well. So there are 3 dimensions associated with each of these and 32 of the pads. That's 96 total. Well, what we did to guarantee control intimacy here is we sampled those gestures at a high rate. And in fact, we sampled them at 1/8 the audio rate, which was near 8 kilohertz. And then we upsampled to the audio rate and sent them to the host computer over Ethernet. I've been playing with this thing now for about 4 years, and it's been behaving very well, and it gives me the kind of feel that I'm after in a live performance setting. I'm just wondering if there's any water up here. No, it's okay. If possible. I think I can make it to the end here, but I may not. All right, so let's go back to this voices, streams, and channels, and so on. And, many people have had experience with Ableton Live. And Ableton Live can also host, it's a digital audio workstation abstraction that very, very convenient, and it's a very attractive piece of software. A lot of people use it. It interacts nicely with the Max MSP environment that we like very much. And I wanted to say something about the fact that Ableton Live does support parallelism, does support multi-core use, and so does MSP. In other words, we could turn on parallelism in MSP, and we could turn on parallelism in the Ableton Live environment, but then we'd actually parallelize the program. In other words, we would probably oversubscribe thread resources and so on. So some care has to be taken. And one of the really nice things that came out of the ParLab was a solution to this problem with an environment or a system called Lithe, which is incorporated into the tessellation operating system. So if you have the ability to go parallel in many parts of your program, you might, in fact, oversubscribe thread resources and end up with a situation that doesn't perform nearly as well as a single thread approach. So we've got to manage and have a kind of cooperative scheduling policy, and that's what happened in the Lithe framework. I think it probably was live with, I was hope was covered somewhere in the previous days here. Now, one of the things that we're very proud of and has played a role in building a functional, well, we think that functional programming, I mean, it shouldn't be a religion, but on the other hand, it can really help implementation a lot. And Open Sound Control has led us to develop a very nice functional programming environment called ODOT. And I won't be able to go into that very much, but the important feature is this is a messaging system that we can send control data with. It's got a pattern matching language in it, and moreover, and really important, it has high-resolution time tags, which are based on the IEEE 1588 specification, which is also the specification for time in the AVB protocol. So we like to think about building many channel audio systems, arrays of speakers and microphones and so on. And when you have hundreds of channels, you can see that the bandwidth requirements are going to go up, and latency may be becoming more and more of a problem. So this is a non-trivial situation for computers to get into. And but to show you what that means, here's a loudspeaker that we built over at CenMat. This was supported by Meyer Sound Laboratories, which we were very thankful for. And it's a icosahedron. That's a 20-sided object. And the facets of the icosahedron are triangles and can hold, as if you had a rack for a billiard table, you could put 6 balls in there this way. So we filled each of the facets with 6 tweeters, or high-frequency drivers. And each of them, on the other side of each of those tweeters, is a digital amplifier, and so on. And they're all independent one from another. So all 120 loudspeakers in this particular case are separate. Now, are independent. And then we have another mid-range system, which is not shown here, which has 12 drivers on it and so on. So we end up with a fairly large channel count to handle here. Now, one of the goals of this particular speaker was to allow us to control, in real time, of course, the radiation patterns. And we used a spherical harmonic representation for that. And we primarily worked with beams that we farmed from this. And then we would move the beams associated with different voices. Our idea was to somehow make the electroacoustic source here, behave in some sense like a traditional musical instrument that radiates in a very different way depending on what notes are being played and so on. So if you think about a saxophone, for example, playing a scale, when we're at the bottom of the scale where all the pads are closed, we have the sound emanating from the bell, and then as we open up the sides of the instrument or the pads, the sound begins to emanate from them, and so the radiation pattern is changing dramatically, and so the engagement with the room, with the environment, is time varying and so on, and that's the kind of thing we're able to achieve with this device. If you want to hear it sometime, come over and visit us for one of our concerts over at the Center for New Music and Audio Technologies at 1750 Arch. Now, this is a project that we were beginning to work on, but now we're much more equipped to do it. And so I wanted to say that we're getting back onto this. We're really interested here in having room quality assessment and room simulation rendering engine sort of work together. So we could say, let's have the room behave this way. And I can say that if you think about the kind of thing that's going on in Zellerbach Auditorium these days, Meyer Sound has a system in there with many inputs, many microphones located primarily in the ceiling area and so on, and many small loudspeakers, and they're all quite nicely cached away. You really don't, if you haven't been told about this, you wouldn't know it's there. And so they're able to simulate various kinds of reverberant environments using this system, which is known as the constellation system. Well, we're really interested in this kind of assessment and simulation working together. This is some work that Eric Battenberg did for his thesis. He was really interested in having a system that would recognize certain patterns on his drum set. And he did some audio feature extraction. And one of the key ideas in this particular system was the use of non-negative matrix factorization to do source separation. And that's the thing I want to emphasize right now. He did a parallel implementation of that. Later on in the thesis, he got into using deep belief networks and so on. And again, parallel implementations of them primarily on GPUs. So non-negative matrix factorization is explained here briefly. You can think of the spectrogram, which is on the left, as being the product of two matrices, one of which contains the frequency regions and so on of the various sources that we have. And here we're trying to separate a hi-hat from a snare drum and a bass drum. So take the sound apart. And so if you factor this spectrogram, you can pull out these two matrices and have them positive. So this was a real speed up put in shape by exploiting GPU and parallelism to do this very, very important task in audio source separation. So here's a kind of description of how Eric used the pattern approaches that Kurt Kreitzer's group emphasized a lot in the ParLab work. And so here's a kind of list of the various features, how the various computational architectures played a role in how many, and dwarves play a role in the various features of that program. I'm going to end by thanking some of the contributors, namely Meyer Sound Labs, Remus, and Adrian Fried. Andy Schmieder, who was with us early on, was really, really productive in working on the loudspeaker and the radiation pattern synthesis. And Eric Battenberg did a wonderful thesis. And he's now working for a music information retrieval firm. He's over at Gracenote. So here are the resources. You can grab them. I really urge you to look at our site and cinmat.berkeley.edu. So thank you. Any questions?
I have a question.
Now I've got to run to another talk.
I have a question.
Yes, go ahead.
For the non-negative matrix factorization,
yes.
Is that possible only because the drum signal is periodic, or why would
you
be able to do that?
No, it wouldn't necessarily. It doesn't have to be periodic. No.
So what was it that allowed you to factor it like that?
What? Excuse me?
What was it that allowed you to factor the matrix in that form?
That's an interesting question. I've seen this applied to lots of different kinds of problems. I've used it in conjunction with trying to separate signals like flutes from string instruments and so on. I've also used it I'm trying to think of what would, if we didn't have good models of if we didn't have a good idea of what we were going for in the sources that we're trying to specify, I think we'd end up with a fair amount of trouble. In particular, if the sources varied a lot from, let's say that one drum had a different kind of sound every time you hit it, or the drummer was playing it near the rim sometimes and then the center and so on. So it would lose its integrity as a sort of identifiable source. I'd say that would be the one key. And then they have to be positive, these matrices.
But for a spectrogram like that, it's always going to be positive,
yeah,
right?
That's right. Well, If there aren't any other questions, thank you very much.